In this video, we're going to integrate this double integral. In our case now, our function f of xy is 1 over 1 plus x squared plus y squared. And the d, or the domain that we are integrating on, is the set of xy in r squared such that x squared plus y squared is less than 1. That means in our case here now we have this disk. Okay, so this is in the xo plane. Okay, so this is x, this is the origin, this is y, and this is z. Okay, in our case now, to make this integral easy, we're gonna switch to polar coordinates. Okay, because here it's not easy to integrate, because if we want to do integration without using the polar coordinates, we will have to fix x and change y. In this case, x is going to be between -1 and 1, and y is going to change between two functions. Okay, on top, on the positive part, okay, the positive part, we're gonna have y is equal to the square root of 1 minus x squared, and the negative part, y is gonna be minus square root of 1 minus x squared, and we have to split this region into two. Okay, in fact, we're gonna do it in two parts, this one here and this one here. But the polar coordinates will make this one easier. Okay, in our case, if we let x be r cosine theta and y be the r sine theta, okay, here we see that x squared plus y squared is less than 1. That means r is between 0 and 1. Okay, when we do that here and using the fact, this fact here, okay, theta is going to be between 0 and 2 pi. Okay, and we know that Jacobian in this case is just given by r. The Jacobian is given by r. Okay, and therefore when we switch, okay, the polar coordinates, we're going to integrate on this region here. Okay, so here r is changing between 0 and 1, and theta is changing between 0 and 2 pi. When we do that, we're also going to change this one here. Okay, in this case, our function will be 1 over 1 plus r squared, because x squared plus y squared is equal to r squared. Okay, therefore my integral will be the integral between 0 and 1 and 0 to pi, 1 over 1 plus r squared, and the Jacobian will be r, and dx dy will be dr d theta. Okay, and now I can see that I have two functions that are independent of each other. So r doesn't depend on theta. Okay, and therefore in this case I can integrate without worrying about anything. Here, integral between 0 and 1 of r over 1 plus r squared dr times the integral between 0 and 2 pi of d theta. Once I do that, I'll do this one first. It's easier. I have 2 pi times the integral between 0 and 1 of r over 1 plus r squared dr. And this one, and now that's the natural log. So this is 2 pi. So I need 1/2 here. Okay, I need 1/2, 1 over 2, the natural log of 1 plus r squared between 0 and 1. Okay, so now when I do my integration, I'm gonna have 2 pi 1/2 the natural log of 2 minus the natural log of 1, which is 0, and therefore I have only pi the natural log of 2. Okay, so here in doing this integration, I have used something that we know. okay, if I'm integrating a function on some domain, okay, and that function f of x can be written as two functions. So f of x can be written as the product of some function, let's call it h, that depends on x, and g that depends on y only. When I do the integration, okay, I can split this integral, okay, into two. Here, if I have this integral on d is between a and b, so if x is changing between a and b, so I have the integral between a and b of h of x times the integral between c and d of g of y dy. Let's do these ones for the clarification. So this is what I have here, okay? And the polar coordinates are very helpful. Like in this case, try to do it this way here by splitting this function into two and integrating, okay? You will see that it will be difficult to evaluate. But with the polar coordinates, it's easy to do. Okay? Thank you very much. If you see any errors or mistakes, please let me know. Thank you.